So what is a buffer overflow? If you've ever done programming of any type, variables for a function call are stored in memory. What's interesting is the order in which they're stored in memory. So for this video, we're going to be doing this using Kali Linux, which is based on Debian. Now the details of how variables are stored in memory will change a bit between the platform, the operating system, as well as how the program was compiled. In this image here, this is upper memory. This is the highest memory address. So if you have 4 gigs of RAM, this is the top for it. So at the high memory, which is up here at the top, versus the low memory, we can see the stack layout. So we have argv, which is the arguments being passed into the function, argc, which is the count, the int value, the return address, in other words, where the function should go next after it's done running, the callers, ebp, also known as the frame pointer, which is basically saying, now that we've returned, where do we go back to? A little bit of alignment space, because again, we're dealing with a 32-bit processor or a 64-bit processor. Things generally will run faster when things are aligned to the memory address, which is a power of 2, 4, and 8 respectively. And then our buffer. This buffer right here is what we're going to be exploiting. And then way at the bottom, we have the value ESP, which is the stack pointer, which is made to point to the quote-unquote top of the stack, which is actually the lower memory address. So we have the top address and we have the bottom address. Now EBP stands for the extended buffer pointer. These are register values in the processor itself. So if this extends to things like Intel processors, AMD, ARM, it's a general way of kind of managing how the stack itself is used and referenced on the assembly level. So if you've never programmed in C before, this is actually a really simple program. We're going to go ahead and do an include for the standard input-output header, which allows us to read and write from the standard library. We're going to import the library for string. That's it. Quick and easy. By default, C programs call the int main function, and the default values passed to that are int argc, which is the count of arguments being passed to it, as well as the character pointer to argv, which is a character array of values, basically a string. So the next line, we have a char buffer with 500 bytes, and we run the very vulnerable string copy. This says copy the argv value and the first value that we passed to argv, and then copy that into buffer. Now the problem with this function call is that if argv is more than 500 bytes, it will overflow the buffer. Now you can see in this diagram, we start writing in the lower memory address. So when the function is first created, it writes from the high values down to the low values. And the assembly code that we'll go over a little bit later tells it to give itself around 530 bytes. So we start at the lower value here, we actually write up. So what ends up happening, we actually end up overwriting things like the caller's EBP value, the return address. And this is where the danger comes. So let's exit out. So in our home folder, we've got our env exec.sh, we've got our vuln.c. Now we're going to compile this using GCC to create an executable file. Okay, so now we have our vuln executable or ELF file. In order to properly debug this and show the vulnerabilities, we're going to call env exec.sh and send it the command -d vuln. What this will do is clean up our bash environment and strip it of every setting possible, except the ones that are required. and then run the GNU debugger GDB, loading up the file vuln. Now we're inside GDB, so we're gonna go over just a couple of things, some of the common commands. So you can type things like quit, obviously, to get out, press up to restart it, get back in. You type Control L, that will clear the screen. Type list, which shows you some of the debug symbols. So we have like right here the debug symbols for C code. Do a list main, do it based on function calls. We can actually disassemble this by typing disas main. This will show you the assembly code that's powering the function. So if you look right here, you'll see a hex value, which is 0x1f4. If you converted that hex value to a decimal value, it's 500, which indicates the size of our buffer. So just know that our string code right here, char buffer, is being allocated right there with that assembly call. Info functions shows us all the various functions. So you can see, even though we just defined one function, there's other functions floating around in there. These are all the global variables created by C automatically. So let's go ahead and run and pass our program the value hello. Okay, so we ran the program and it exited normally. Nothing super interesting. Instead, let's go ahead and try overloading it and causing it to crash. So what this command is actually going to do is a $sign parenthesis is going to create a bash subshell, and it's going to call Python, and -c is the command, so it's going to go ahead and print x41 508 times. x41 is the hex value for the A character. So because the buffer was defined as being 500 characters, we're going to pass it 508 characters and overflow it, and this should crash the program. So go ahead and run that, and we can see we just received a segmentation fault. So let's go ahead and look at the registers. And again, we're looking back at some of our ESP and EBP values here. So we passed this thing the value of 41, and you'll notice that our EIP, or extended index pointer, and the EBP, the extended base pointer, have both been overwritten with the values 41, 41, 41, 41. So what can we actually do with this? Well, let's look at the memory addresses. 200x characters, parentheses, $sign, ESP. In other words, take the address of the extended stack pointer, go back not only 500 characters, but let's go back 550 characters. So let's go back a little bit before that. So run that command, and we can actually scroll through the memory itself. So if you look here at this address, you'll notice it's the very beginning of where our 41414141 sequence started. If we press down to return, we can see where the buffer itself exists in memory and where it was being overwritten. In order to actually make this exploit work, we're going to need to take control of the extended base pointer. So instead of typing in 41, which is the ASCII character A, we're going to type in the character 90. The reason why is in assembly, the hexadecimal 90 is a no-op, or a no operation. In common usage, the no-op command is used purely for padding purposes. It doesn't really do anything. It's really the equivalent of just saying go to next, go to next, go to next. So because we know we could crash a program with 508 bytes, we're going to say print 90 426 times, and then we're going to pass it this hex value, which is the hex version of running bin-zsh, which is another shell type synonymous with bash. So in other words, we're going to have we're going to have our vulnerable program run our another program. So this is what's referred to as our shellcode. So what this is going to do is going to fill up the buffer. It'll overwrite the alignment space, and our goal here is to overwrite the caller's EBP as well as the return address, but the value is 5151. If we do this correctly, we should see the register's EBP being overwritten and the EIP being written with the value 51. So we're going to type Y. So again, we got another seg fault, but this time the return value was 51 instead of 41. So that means we were able to successfully overwrite the return address as well as the caller's EBP. EIP and EBP have been overwritten. Now this is good because we know how large the buffer is and how many bytes we have to overwrite afterward to change and control the EBP value. So why does this actually matter? It's because the return address and the caller's EBP, we can tell the program is running in memory to actually go to another memory address. By default, this will go back to the function that called the int main function. But instead, what we're doing, instead of going back to the parent function, we're going to redirect it somewhere else. We're going to redirect it back into the buffer, and within the buffer, we're going to be using what's known as a NOP sled. We're going to pass the value 90, and we're going to keep sliding and sliding and sliding until we hit our shell code to run another shell, which is a bin ZSH. So one of the things that we have to do first is double check our memory. Here we can see the value 90, so our NOP sled does in fact exist. And we're going to have to choose a value. We're going to have to choose some place in the middle of the NOP sled here to run. So let's pick this value right here, 0xBFFFFABA, right in the middle of our NOP sled. So what will happen is if we can redirect the execution of the program to look at and start reading this part of memory, it'll continue sliding until it hits our exploit. Now one of the things we have to do first is convert this memory address value here into big Indian. So we have to reverse the order of the bytes. So BFFFFABA becomes at the very end BFFFABA. It's not exactly reversing it, but it's similar to reversing it. Anyways, so here's our padding for the NOP sled, and then our payload, and then way at the end, instead of using the value 51, we're going to use this specific memory address. So if we run this successfully, we should see a new shell. So type Y. So now we see Cali #. So if we type in who am I? Well, I'm root. PWD, what is our present working directory? Do an ls. There you go.